Dear students, in the last lecture, we have discussed this atomicity, means how to calculate gamma for gases, different gases. And here, in most of the cases, I have calculated Cp and Cv by considering only translational and rotational. So if examiner has asked, okay, consider vibrational also, then you have to consider vibrational. Otherwise, leave the vibrational because the contribution of vibrational is low compared to the translational and rotational, right? So I think it is clear to all of you. And I have also defined this what is delta E and what is delta H. Basically, both are energy, but they are defined in a different way, different manner. One is defined at constant pressure, delta H is defined at constant pressure, but internal energy is defined at constant volume. So this is the little revision. Now in this class, I will start from this calculation of gamma of mixture of gases. Suppose that if you have a system like this, here you have helium, a monoatomic gas, and here you have nitrogen, a diatomic gas. Suppose that both were kept at temperature T, okay. Behavior of both is ideal. Here and N1 moles of this helium and N2 moles of nitrogen, heat capacity at constant volume CV1, and here this is CV2. Definitely both have different CV values, right? Suppose that these two gases were mixed. N1 and N2 moles were mixed. Right? So now in the mixture, all of you are knowing that there is no reaction between He2 and N2. So the total moles now, and the temperature is same. At the same temperature we are mixing, right? Okay. So the total number of moles now N1 plus N2, right? And let the CV of this is CV mixture, right? So we have two different gases at the same temperature, and different quantity, means N1 and N2 moles are there. They are mixed at the same temperature. So very easy calculation here. Now can you write this energy? I mean energy you can add or subtract. So what energy you are getting in this mixture from here, and what energy you are getting from this in this mixture, you can add. So you can write a very simple relation: energy of this mixture is equal to energy of helium plus energy of nitrogen, right? This is basic equation. Energy of mixture, you have formula NCV delta T or T, right? Because temperature is same. So CV mixture and N1 plus N2. So here you can write N1 plus N2 CV mixture into T is equal to N1 CV1 into T plus N2 CV2 into T. Simple. You can write this. Now see this T and this T cancel. So you have N1 plus N2 CV mixture is equal to N1 CV1 plus N2 CV2. CV2. This is your equation 2. Right? Any doubt? Very simple equation. Now you have formula Cp minus Cv is equal to R. So you can write here Cp by Cv minus 1 is equal to R by Cv. And all of you are knowing that Cp by Cv is equal to gamma. So gamma minus 1 is equal to R by Cv. So Cv is equal to, you can write R by gamma minus 1. This is another equation. Now use these two equations, equation 2 and equation 3, you can write N1 plus N2. Cv mixture you can write R by, because R is same for mixture and for pure, by gamma mixture minus 1 is equal to N1 CV1 you can write R by gamma 1 minus 1 plus N2 R by gamma 2 minus 1, right? So this R is also cancelled. So you can write here sigma Ni by gamma mixture minus 1 is equal to N1 by gamma 1 minus 1 plus N2 by gamma 2 minus 1. So this is the formula through which you can calculate the gamma of mixture. Clear? All of you are getting this formula? Now see one more formula you can derive from here, this equation 2. You can from equation 2 you can write, from equation 2 we can write Cv mixture is equal to N1 by N1 plus N2 Cv1 plus N2 by N1 plus N2 Cv2. So you can write here X1 Cv1 plus X2 Cv2 Cv mixture. So this is equation 4, right? This is equation 4. Similarly, you can write Cp mixture is equal to R plus Cv mixture. Equation 5. Now from equation 4 and 5, from equation 4 and 5, you can write Cp mixture by Cv mixture is equal to gamma mixture. So this formula also you can use to calculate the gamma mixture if you have Cv mixture and Cp mixture, right? If you have Cv mixture and Cp mixture. So these two formulas you can use to calculate the gamma for the mixture. For example, suppose that 2 moles of helium and 3 moles of nitrogen are mixed at 300 Kelvin. Find gamma for the mixture. Right? Find gamma for the mixture. Okay. So you know CV for the helium. CV for helium. This is equal to 3 by 2R. Right? Or and CP for helium monoatomic 5 by 2R. So what is the gamma for helium? Gamma for helium, this is equal to 5 by 3. So this is 1.66. See here 1.66 monoatomic 1.66. And this diatomic nitrogen. So similarly you can calculate for nitrogen as well. So for gamma for nitrogen you can directly write 1.4. Right? So now you have gamma for nitrogen, now you have gamma for helium. So you can and moles of helium and nitrogen. So you can use the formula N1 moles of helium plus moles of nitrogen by gamma mixture minus 1. This is equal to moles of helium by gamma of helium minus 1 plus moles of nitrogen by gamma for nitrogen minus 1. Right? So 3 and 2 total 5 moles. So 5 by gamma mixture minus 1 is equal to 2 by 1.66 minus 1 plus 3 by 1.4 minus 1. So this is equal to 2 by 0.66 plus 3 by 0.4. Right? So 2 by 0.66 is equal to 3.03 plus 3 divided by 0.4, 7.5. So 7.5 plus 3.03, 10.53. Right? So you can write 5 is equal to 10.53 gamma mixture minus 10.53. So this is equal to 15.53 gamma mixture is equal to 15.53 divided by 10.53. 15.53 divided by 10.53. So this is 1.47. 1.47. So this is the answer. So in this way you can calculate the gamma for the mixture. Right? Hopefully all of you are clear how to calculate this gamma for the mixture. Okay. Good. Now, see, let's start this first law of thermodynamics. The correct statement of this is the energy of the universe is conserved, right? This statement was given by Clausius. So this is the perfect statement of first law. Many people casually say, okay, the first law is the law of energy conservation, but the question is that at in every type of system energy is conserved. The answer is no. Whenever you take an isolated system, then only the energy is conserved, and universe is the best example of isolated system. So when you are writing thermodynamics first law definition, so extra care should be taken regarding the system. If your system is not isolated, your this statement is not valid. But see, it is so popular, law, that you just say, okay, energy is conserved in the process. So it is assumed that the system is isolated, and until or unless you are not assuming that your system is isolated, your first law is not valid, right? So every time when you explain this law, first law, keep in mind that your system should be isolated, and this word should be come to your definition directly or indirectly. Like here, I'm here use this definition indirectly. Universe means this system is isolated, right? Experimentally, we found, see, experimentally we found that experimentally experimentally we found that that delta W plus delta Q. So here, this is default that when in chemistry I am talking about this, W means WPV basically. This is equal to 0. See, means the in any cyclic process, this is the symbol of this cyclic process. In a closed cycle, the sum of PV work and heat change, this is equal to 0, means the sum, right, W plus Q, W plus Q is independent of path, is independent of path, independent of path, right? So this implies that there is a state function whose differential is this, right? And that state function is called what? Internal energy. So you can write delta E is equal to delta Q plus delta W. So this is the mathematical statement of what? Thermodynamics first law. So this state function of which differential is this, that is the internal energy, right? And for delta E for cyclic process, this is equal to 0. So this observation is justified by this, right? So this internal energy is, this is for cyclic process, this is equal to 0. So delta E is equal to 1 to 2 dE. This is equal to E2 minus E1, right? And this is equal to Q plus W. Does not depends on the path. Does not depends on the path, right? So individually these two are path what dependent, but we can say that this Q and W are the ready for sacrifice. Means Q and W are sacrificing in such a way that internal energy becomes constant, becomes path independent. So Q and W, these two functions are you can say ready for always ready for sacrifice, so that state functions can be uh, be path independent. State functions can be path independent. So for fix value of so we can write here as the state function property of state function. So we can write here E is the function of T and V for given moles of for fixed n. So you can write this. This is what state function. Internal energy is a state function, and this is extensive. Right? Means scales with the system size. Extensive means scales with the system size. System size means if you subdivide the system, this will change. But if you take this E by N, this is called molar internal energy. Internal energy. This time it is intensive. This is intensive, right? So this is what Q plus W is a state function, and that is given by this new thermodynamic function that is known as internal energy, right? So in this way we can explain the thermodynamics first law, right? Law of energy conservation. Now see how to justify this statement. And if for any cyclic process, if you are writing thermodynamics first law, mathematical expression is this. This is the mathematical expression of the first law. Basically, this is the mathematical expression of the first law. So for a cyclic process, if you want, you can write, or for any kind of process, you can change in this equation and get the desired equation. Now see how to justify this that law of energy conservation. See, suppose that if we have a system, and in the system we have suppose that there is some processes going on in the system. Suppose that gas is expanding or compressing, whatsoever phenomena is happening here, and the wall is diathermic, so that heat easily can be transferred between systems. So this is system and this is surrounding, right? So you can write this equation, delta U of system, if delta U of system is equal to delta Q plus delta W PV, this equation. Suppose that gas is expanding and temperature is constant. So if gas is expanding means gas is doing work, then how temperature is constant? Because the equivalent amount of heat will be transferred from surrounding to system. So the energy of the system increases, so Q is positive, right? And system is doing work, so this minus PV, when we do the formula, then we put the that minus PV, but here we should write plus W. When you replace this, then you can write minus P external dV, right? But I am writing this work only here. So gas is doing work, equivalent amount of heat is transferred from surrounding to system, so that the temperature of the system is constant. So what is the change in the internal energy of surrounding? So you can write delta U of surrounding is equal to minus of delta Q minus of delta W. This is equation 2. All of you are getting this point or not? Whatsoever work is energy of the system is changing, the equivalent and opposite of the surrounding will change. So we can write here delta U of universe means isolated is equal to delta. Oh, I am writing here U, not E, so I can change this delta E. Oh. So this is equal to delta E of system plus delta E of surrounding. And we have already cleared that two ways we have for a closed system in which there is no change of moles. We have two way to change the internal energy of the system. One is heat change, another is work. So that's why I'm considering these two here. So this is equal to delta Q plus delta W PV, right? Plus minus delta Q minus delta W. So this. So this is equal to 0. Right? So energy of the universe is constant. Means imagine if you are doing some process, you are demonstrating some process in a system. Let the energy of the system is changes by E unit. So equivalent, suppose that energy of the system increases by E unit, so subsequent decrease in the energy of the surrounding by E unit. So this is called what? Law of conservation of energy, but this you can prove in this way to demonstrate that this first law of thermodynamics is basically the law of energy conservation, right? So now we have different formula for this. Now see, We have one formula for delta E. Delta E is equal to delta Q plus delta W PV, right? Pressure volume work. Okay. And in a general statement, we can write some other work if along with this PV work is happening inside the system, then we can also write that work also here. Not only PV work, but any kind of work. So I am putting here one more type of work in the thermodynamics first law, right? Means this thermodynamics first law is not telling that only PV work we have to consider. We can consider any kind of work. So now I am writing a general statement, right? General statement, and this is equation 1 dash, right? Here we have I have taken this equation 1. So now a general statement of first law. General expression, right? General expression. What is this? This is called operator work. This is called operator work. This is PV work. So along with this PV work, any kind of work we can add here. It is not that only PV work, right? So this is called operator work. So along with PV work, some operator work may also takes place in the system. Right? So this operator work is always called useful work. Useful work. Now I'm taking one example to explain you the difference between useful work and non-useful work, right? Suppose that you have a large cylinder in which gas is enclosed at a high pressure, and you want to suppose that if you want to lift some mass up to the first floor of your building, and you have made one arrangement, then you have taken a cylinder in which the gas you have taken, and now you can put some whatever mass you want to lift up to the first floor, you can put that mass over the piston. What will happen? You have taken high pressure, means pressure inside the system is more than the external pressure, so that will lift the mass against gravity. So in this whole process, two types of work are taking place. One is gravitational work, lifting of mass to the first floor, and another work is also simultaneously taking place, that is PV work. That is PV work, expansion. Gas, some energy, some amount of energy of the gas is expanding, used in the expansion of gas, and some energy used to lift the mass. So expansion against 1 atm pressure, because we normally consider the one atmospheric pressure is the external pressure, atmospheric pressure. So the work against the atmospheric pressure was not our useful purpose, because that energy is wasting. For that purpose, our aim was to lift the mass up to the first floor. We don't want to use the energy of the system for expanding the expanding against the external pressure, atmospheric pressure. So whatsoever the fraction of energy used in the expansion, that is non-useful for us. Similarly, now we can take another example. Suppose that in a container we have taken a reaction, gaseous reaction we set up. During the course of reaction, energy is required. We are giving the energy to the system to break the bond and to make the reaction happen. But that energy, if some part of that energy is consumed in the expansion of our system, means pushing the piston of the system upward. Suppose that we have taken constant pressure system in constant pressure system like CP. Earlier we have discussed. So if you you are putting energy to the system to break the bond, to make the reaction happen, and that energy is consumed to lift the piston against the atmospheric pressure. This is not your purpose here. Your purpose is to break the bond. So whatsoever energy present in your system, that is used in two ways. First, for useful work, that is I have referred here operator work, and that one part of energy, some part of energy that will go to the expansion of the system against external pressure, that is atmospheric pressure. So that in chemistry we don't want to do this expansion. We want to make the reaction. We want to perform our reaction. So this PV work is termed as a non-useful work in chemistry, right? So pressure volume work, WPV, is called non-useful work. Non-useful work. So sometime you will come across to this terminology. So non-useful work is the PV work, and operator work, operator means operator, whether you have taken robot or some person, right? That is operator work. Whatsoever work done by that system, that person or living person, or you are using a robot. So robot is also requires some energy, battery it is required. So this is called useful work. So in every system or in this in chemistry, when we perform our reactions, different processes, we try to make what constant pressure system. So in constant pressure system, fraction of energy is always consumed to lift the piston, right? So the work against because you are not able to remove this atmosphere, you are not able to remove this atmosphere. This is not in your capacity. So since you are not able to remove the atmosphere, so you cannot remove this work, non-useful work, from the system. This is always there. This is always there until or unless you are not taking constant volume system. And if you take constant volume system, there is some problem for the chemical reactions. When you take constant volume system, the monitoring problem is there. When you open the system, there is some loss of material. How to observe your system. And one more thing, if you are taking constant volume system, pressure shoot up very high, and if pressure is very high, if the wall of the container are not so strong, then there is a case of danger. So usually we prefer constant pressure system for monitoring any physical or chemical change, not the constant volume system. So constant volume system are not the practical systems. Practical systems are constant pressure system, and everything is happening around us under constant pressure system, and that constant pressure is the atmospheric pressure, right? So this PV work is called non-useful work. because we cannot remove atmosphere, and against atmosphere some expansion work is taking place in the constant pressure system, and this is called operator work. Okay, if you are not considering operator work, then your equation reduced to this only, and if you are not considering this, then your equation to this. So basically we first here uh, at your level, we try to first, I mean, to familiar you how to calculate this PV work. But I am giving you a general statement, general expression for the first law of thermodynamics, that it is not restricted only PV work. It includes any kind of work, and so we can classify the work PV work and non-PV work, right? So this you can say operator work, useful work, or non-PV work, non-PV work, right? You can also this classify as a non-PV work. So non-PV work is useful work, and PV work is non-useful work, right? So see the same situation. So this I mean our system has compulsion to do this work, compulsion, because we cannot expel the atmosphere, right? So against 1 atm pressure or against atmosphere there is some work, and this is the compulsion of the system. That's why it is non-useful, right? And this concept is applied on you people also. Those students who are studying, or who are I mean do the study in some compulsion, their work is not useful until or unless you are not happily involved in the studies. Your work becomes what, non-useful, like PV work. So try to make your work useful, and it is useful only when you are by own, you are trying to study, not in the compulsion of your parents or some other, right? So this is what a general statement of thermodynamics first law, very general statement, and I have tried to clear the concept of useful and non-useful work, right? Good. Well, see, so we have discussed, developed the idea about the first law of thermodynamics, and three different parameters: internal energy, heat, and PV work. So now I'm going to discuss isothermal gas expansion. Means when gas, ideal gas isothermally expands, then what are the different parameters? Means Q, W, and E. I am talking about these three parameters, right? Going to talk. So first I am defining the process. First I am taking, irreversible. If your process is irreversible, right? Suppose that gas A is a gas P1, V1, and T. From this initial state, it is moving to a gas P2, V2, and T. P2, V2, and T. This is the final state, and this final state with the fix n is fixed, means moles are fixed, right? T is same. This is isothermal, basically isothermal change. This is initial state, this is final state. So how you can achieve this irreversibility? So there are many ways to achieve this state. First we can take P external is 0. Suppose that we are taking a gas. Here this is P1 is the initial pressure of the gas, P2 is the final pressure of the gas. and some external pressure is required, external force is required, otherwise there is no work. If P external is 0, means this type of expansion is called free expansion, free expansion, or expansion against vacuum, or expansion against vacuum, right? So when you take this, whenever P external is 0, and suppose that you have gas in a cylinder and P external is 0, when you remove the external force, gas will suddenly expand. So the process is so fast that it is always irreversible. So whenever a gas is expanding against vacuum, or in case of free expansion, the process is irreversible. The process is irreversible. One thing is clear. Now if P external is 0, then W is equal to minus P external 1 to 2 dV, and this is equal to 0. Means gas has gas has done no work. No work means no energy loss. No work means no energy loss. No loss in energy, and temperature is constant. So in free expansion or expansion against vacuum, there is no work is done by the gas, right? So there is no work. And what about delta E for this process? The delta E is also equal to 0. Why? Because temperature is constant, and all of you are knowing that internal energy change is the function of temperature only for ideal gas. So delta E is equal to 0. No change in internal energy. No change in internal energy. Right? Clear to everybody? No, there is no work. There is no change in internal energy. Then delta Q is also equal to 0. If there is no work, if there is no change in internal energy, then delta Q is also equal to 0. You can use this equation, Thermodynamics first law. Delta E is equal to delta Q plus delta W. Right? So if del WPV is 0, delta E is 0, so Q is also 0. So see all these parameters in a free expansion, or you can say, expansion against vacuum. So in the expansion against vacuum, there is no work, there is no PV work, there is no change in energy, and there is no heat change. Means nothing is happening here. Means there is no control of energy here. Then why this change is taking place? Which is the controlling factor? So which is the controlling factor here? So what is the controlling factor? Controlling factor here means which factor is controlling this type of expansion, because expansion is taking place whenever you take a gas and you open the gas into the vacuum. The process is so fast, gas will expand immediately, but there is no role of energy. There is no role of energy. Energy is not driving this process. So what is driving this process? What is the controlling factor? This is a big question for us. and I will answer later on this, right? Not right now. So all of you have to wait this, that which thermodynamic function controls this type of process in which there is no energy change, nothing to be changed with the respect of energy, but the process is happening, right? And process is moving in a particular direction. So I will answer in the same chapter, but for this you have to wait for some time. Now this is one way to get the irreversible process. Second, you can change this, you can take P external is equal to P2 in one step. In one step, if we are doing this change, what I have written here from this state to this state in one step, then that is also irreversible. If you are doing in two step, also reversible. If you are doing in three step, also irreversible. But if you are doing the same change in what infinite steps, then it becomes reversible. So one step, two step, two step, or three step, three step. So the process is what? Irreversible. Right? So suppose that the work involved in this is W1, in this case W2, in this case W3, then can you let me know what will happen to the what is the order? So definitely W3 is maximum, then W2, and then W1. So if any, you have to compare the magnitude basically here. So if you do the irreversible process in one step, if you are doing the same irreversible process starting from the same initial state to the same final state in two step or in three step, then this is in three step, if you increase the number of steps, obviously the work will be increased, means work accordingly increases, right? So see, in three step, basically more work will be delivered to the surrounding compared to the two step, and in two step more than one step, and all these steps are irreversible. Now see the second case, and the formula, all of you have the formula for this work. W delta W irreversible initial state to final state is equal to minus P external dV. P external dV 1 to 2, and this P external is equal to P2, which is a constant. So you can write here minus P2 V2 minus V1. So there is some value for W irreversible, right? So W irreversible is equal to this. So you can say that okay, it is less than 0, means not equal to 0, not equal to 0. Clear to everybody? Okay. So this formula you have to use to calculate the work in such type of processes. So this is for work. This is work. Okay. Now, what about delta E in this process? Then what should be the delta E? Delta E is equal to 0. Why? Why delta E is equal to 0? Why? Because T is constant. T is constant, so delta T is equal to 0 and delta T is equal to 0. So I have given you the master formula for delta E is equal to NCV delta T, right? So if T is constant, then delta E is equal to 0. So delta E is equal to 0. W irreversible is not equal to 0. It is less than 0. It is less than 0. So what about delta Q for such process? So delta Q is equal to, you can find out with the help of thermodynamics first law, delta Q plus delta W. Delta E is equal to 0, so delta Q is equal to what? Minus of delta W, right? So, and what is this delta W? This is negative, less than 0, so this is more than 0, but not equal to 0. So this is what? Delta Q in a irreversible process, isothermal irreversible process, right? Heat change, it is greater than 0, work, it is less than 0, and this is, I am taking what? Expansion, right? So here I am taking here what? Expansion work, not compression. Expansion. Clear? Okay. Now the second case is come to the reversible. Second case is reversible. Reversible. See the same gas, A gas, P1, V1, P1, V1, T, T. So this time when this is reversible, so you can write here P external is equal to P gas plus minus dP, plus minus dP. So you can write here P gas, right? dP tends to 0. So all of you are knowing how to calculate the work. I am directly writing the formula. W reversible is equal to minus 2.303 nRT log V2 by V1, right? V2 by V1. So this is again less than 0 and this is not equal to 0, right? So the work in the reversible process, this is less than 0 in case of expansion. Here also I am taking only expansion. Now temperature is constant. Since temperature is constant, then delta E is equal to 0. Delta E is equal to 0 because T is constant and internal energy is the function of temperature only. So what about delta Q? So delta E is equal to, you can write delta Q plus delta W, right? Delta E is equal to 0, so you can write delta Q is equal to minus of delta WPV, and this is negative, less than 0, so this is greater than 0 and not equal to 0, right? So this is heat change. One very remarkable point you have here, that see delta E is equal to 0 in case of reversible and delta E is equal to 0 in case of irreversible also. So you can say here that internal energy change delta E reversible is equal to delta E irreversible, and this is equal to 0 for isothermal process. For isothermal process. Isothermal process, right? So means delta E reversible and delta E irreversible, they are equal. So if a question is put up here, why? So why delta E reversible and irreversible? What are this reversible and irreversible? These are the path, and you know this is a state function. So why this is equal? The answer is this delta E is a state function. State function. So it is independent of reversible or irreversible path. Irreversible path, right? So you can write this. Okay, good. Now see one more important derivation we can do here. We can derive here. See delta E reversible is equal to delta E irreversible, because this is a state function. So we can write here delta Q reversible plus delta W reversible is equal to delta Q irreversible plus delta W irreversible. We can write very easy, no problem. So we can rearrange this delta Q reversible minus delta Q irreversible is equal to delta W irreversible minus delta W reversible, right? Now at this point we can write here, for expansion I am considering, so here we can write minus P external dV 1 to 2 at this point, minus of P gas dV 1 to 2. This we can write, and we can replace this P gas and RT by V, so we can integrate this. So now this is equal to P external 1 to 2 dV plus 1 to 2 P gas dV. Now tell me, for expansion, if there is an expansion, then which term is more? Obviously this term is more. This term, this is W reversible, so this is more than this term. So this value is here positive, because see this minus and minus. So this value is more, but due to this minus plus. So overall in the right hand side, the value is what? Positive. And this will positive only when Q reversible is more than Q irreversible, right? So this is more and this is less. This is less. This term is less. So less negative, more positive here term. So we can write, because you know in the expansion, reversible expansion, more work is delivered to the surrounding. More work is performed to the surrounding, and less work in the case of irreversible. So thus you can say delta Q reversible is more than delta Q irreversible. Means in case of reversible process, more heat is transferred to the system to keep the temperature constant in isothermal expansion. So what we can write here, more heat to be transferred to system from surrounding to keep temperature constant in reversible expansion. Right? So all these things you can justify, right? So from this you can justify that Q reversible means heat absorbed by the system is more in case of reversible compared to the irreversible, right?